Uh, so let me share the screen. Yes.
In post-lunch session, we will have some group photographs. So I will request all the participants who will be available. खुशबू मैम सालिम सर अगर मैं भूल जाऊँ तो आप याद रखना एक हमें ग्रुप फोटोग्राफ लेना है सभी का
ओके सर, ओके। कब लेना है सर?
पोस्ट लंच लास्ट सेशन में ले लेंगे
ओके, फाइन सर, फाइन। ओके,
Okay, sir, fine.
ओके। So is my skin visible?
यस इट इज विजिबल
Okay,
Yes, of
okay,
course.
okay, fine. Very good morning, dear participants. And yesterday we have just gone through the electric vehicle signal processing schematic, and I have told about like the insertions of the pictures and how we have gone through the dynamics of this like electric vehicle. And then we have compiled the model. We have gone through the SCADA also, and the only one block, I should say, the sub panel is remaining in the electric vehicle signal processing SCADA panel. So that is the control center. So just till now, if anyone is facing any problem, or if somebody is stucking, you can ask me now. Till then, I am running my schematic so that I can reach on my SCADA, and we'll be completing the final block, that is the control center. And here we will need to place some more widgets to complete our model. So now it is getting compiled, and yeah, this is the panel, my SCADA panel, and we have completed these all three four soft panels like mechanical transmission, propulsion, battery storage, everything. This we have like completed. Now just for having the last sub panel, that is the control center, I am starting. For this I need to have the sub panel again, and I need to place it here, and I am just giving the name it as control center. Sorry, then I'll tell you what we are just placing, what essential widgets we are placing in the control center. Just name it as control center, and now just let get into this. Fine. And in the control center, we need to have some widgets, and I want to place in the form of the group. So today I will let you know about one more widget that is a new that is I have not taken yesterday. That is the group widget, and in this group widget, you can place your required widget to make it as a like individual panel. You can say individual sub panel. So for this, what I want to do is, like, in this group, I want to name it as vehicle measurement. Just I am changing its name as vehicle measurement. Okay, I'm going very slow. If you are stuck somewhere, you can interrupt me. Yeah. So here I want to place three widgets. The first is the gauge, and two, we want the trace graph. So for this, I I will take a gauge, and I'll go for two trace graphs in this. Yes, and as likewise yesterday, we have done, we will make the we will add our signals in that, in the same fashion we have done yesterday. Say for example, the first one is, this is what I want to measure the vehicle velocity. So I'll change its name, vehicle velocity. Okay, and range should be, I want it to 0 to 60, and the signal I want to add is in vehicle control and EMS section, like we have done yesterday, vehicle speed, this one, vehicle control and EMS in this vehicle speed. Fine. Then at this trace graph, I want to have vehicle requested velocity. So what I'll do, just double click on it, and again, like vehicle requested velocity, and in this I want to make the time window for 200, just to take 20 seconds per division, 20 to 100. Again, I need to add a signal. So I'll go in this, and here in the vehicle control and EMS, yes, so here I require the requested speed in vehicle control and EMS. Uh, Current speed. Just give me a minute. I think I have not placed this requested speed probe in the vehicle control and EMS. Yeah, let me check. RQST speed, RQST current. Yeah, just wait. Let me check into this schematic. Here, vehicle control and EMS. Yes. Yeah. Here I need to place one probe, and that I forgot to place. So just let me take a probe here. Yes. And here I'll need to take one gain also, just to convert it in kmph. This is the requested speed, like USD, and speed. I I need to have one gain block also, and it is for to converting into kmph. Say for example, uh, just to hide its name, I want to hide its name. Oh, sorry, or I should say I want to name it as 2 kmph. Sorry, 2 kmph. Okay, connect here. Yeah, fine enough. So what I'll do now, I'll just run this simulation once again. The control S I have done, and let's compile this once again. Now it will show me, it will show to me on the SCADA panel that in the vehicle control EMS, we will have the requested speed as well. Earlier it was not showing, just because I have not placed the probe, and just to observe the signal in the SCADA, we need to place a probe that I have forgot to place, and I've checked in my schematic model. So this is the way you can, you know, place the probe. Yes, again, Now let first add the signal, and that is in under vehicle control and EMS. Requested current again, it's not coming. I even problem. Why it is not coming? Requested speed. Just wait. Control and EMS. Control S. Control and EMS RQST speed. दिखा नहीं रहा है. Yes. Requested speed. Yeah, here it is coming. Yes. Vehicle control EMS requested speed, and just name it as like vehicle requested velocity. Vehicle requested velocity. Earlier it was not showing because I have not placed the probe, and just in the advanced setting again I'll make the time window as 200, and okay, fine. So this is vehicle requested speed, and in the another one I need to have a vehicle measured velocity. So like vehicle measured velocity, and here I will again add the signal, and this we have to take the vehicle speed in the vehicle control and EMS section. Yeah, vehicle speed, fine. So this is done for the vehicle measurement. Keep saving your panel, and one more I group widget I require. So for that, now let me just make it small so that I can adjust all my widgets. So now I require one more widget, and in this I need to have the group widget once again, and in this fashion I can enlarge it. For this I require one gauge and one trace graph also I require, and here I am having a trace graph. Yes, and I want to show the parameters of the battery storage in this. So just double click on it, change its name as battery storage, and okay. And in this I want to observe the state of charge. So just name it as state of charge. And again, for this, I'll make it 250. And the signal I need to add is in the vehicle control and EMS battery SOC established. This one. So this is for the state of charge in the battery storage section. And again, I need to have the battery SOC percentage in the form of a trace graph. So I'll click on it and just battery SOC. Yeah, it is it actually it is coming in the percentage only. Yeah, so I'll just simply place this and advanced setting is like yes 200 in a time window, and the signal I need to add is the same in the vehicle controller and EMS, this battery SOC established. Yeah, so I have placed the signal, and this is done for battery storage. Now I need to have some parameter for the traction machine, I should say. So the last widget, group widget I require for this, I make it large, not that much. Yes, here I need to have one gauge and two trace graph. Say for example, yes, I need to extend this and just name it as traction machine. Traction machine, and in this I need to have a speed and I want to take it range the range of it up to 2000. Make it 250 and just add the signal. Just add the signal vehicle control EMS DCM speed. Okay, so this widget is also completed now, and this is now here I need to observe in the form of the waveform. So I'll take it as speed graph, and again I will add the signal in this. Wait, just make it 200. Signals that I need to add here is the same only in the vehicle control and EMS, the DCM speed, this one. Yes, fine. The last widget of this model is the torque graph I need to have. And in this, I need to add a signal of like torque. So like add in the section of electric drive, I'll add this DCM torque. Yes, fine. So this is all about the complete SCADA of this. Uh, Now, I first of all I run this model on the virtual hill, then I'll run it on the that real-time simulator Typhoon HIL 402. Just go into the panel route and simply run the simulation. So as you are able to see, the battery SOC is going 90%. This is what the initially we have taken, but speed is the speed is coming after some time. Let me show you. Let me open this propulsion. Say for example, here you can see this is what the signal we have taken, like electric vehicle, once it go to a particular speed and after that it come down to zero as per the traffic and all. So like as you are able to see here in the speed graph, in the torque graph, and the DCM current, everything is coming in the propulsion sub panel. And likewise the DCM voltage and current is getting down. And li- say for example the speed is zero right now, so everything, the DCM current is zero. Now after some time, again, say for example if you're accelerating the vehicle, yeah, likewise this you can see in the speed graph, then all your speed in the form of the gauge you can observe here. The torque is coming. This is the propulsion section. The all the widgets are working here, like the gauges and all. Now if I go to the mechanical transmission, so you can have the tractive force, the vehicle velocity, and the vehicle control and EMS, and vehicle speed is coming here as the signal of everything is getting controlled with the help of the reference speed of the vehicle we are giving. And when I go back to this panel, let me show you the component of the battery storage as well. Battery state of charges you are able to see, as we have taken it initially as the 90%, but as the vehicle is running, the SOC is decreasing as per the battery is getting discharged as the vehicle is running. Now say for example after starting the vehicle has attained a constant speed. Say for example there is no traffic on the road and all, so now we are running our vehicle at the constant speed. This is what the signal we have designed for. And if I go back to this panel route, then I need to show you this control center as well. And in this control center you are able to see now this uh, vehicle current control and vehicle speed. Okay, so this is what I need to show. Now I have shown this to you on the virtual hill mode, and now I want to show this panel on the uh, real-time simulator Typhoon HIL 402. So for this, what I need to do is I am just connecting my real-time simulator with my laptop, and I'll show you the real-time demonstration. Just give me a moment. I am just connecting. Okay, just I have connected the cable. Let me s- close my SCADA first, just because when I'm connecting this hill device, I need to close my SCADA. Then only the device is detected. So just I am switching on my device. So device is getting ready, and for this you need to go into the device manager of Typhoon Hill Control Center. Here, just click on this. Yeah, Typhoon Hill HIL 402 with the help of USB interface I have shown here. And right now I am using the USB cable interface. It can also be connected with the help of the Ethernet, but right now I have connected with the USB cable. And when I am just running this, compiling this model, now it will automatically get loaded onto the uh, Typhoon Hill 402 simulator. Now let's compile the model once again. As you will be able to see, the model is getting loaded automatically because right now I have connected my simulator, and at earlier it was showing the virtual hill mode, and the you can see at the right bottom of your computer screen where I am just placing my cursor. This is right now, this is real time mode just because I have connected with real time, and uh, earlier it was on the virtual hill mode. So now let me run this simulation on the real time mode right now, and it will just show you the real time results. I'm just running it, and here the battery source is 90%. See this, because we have not used the consumption of battery till now. The signal will come after some time. Yeah, DCM speed is coming. Okay, go to the propulsion section. The speed is coming here. Fine. And say for example it's getting down, and you can see the battery storage now it become 89.98. Earlier it was 90%. Initial we have taken the value of this is 90%. In the lithium ion battery we have connected again, and it was we have initiated the initial value as 90. So in this case, they are again, you can see in the case of control center, this recently we have made this block, and you can see the vehicle velocity and everything's getting rising. State of charge is getting reduced now 89.94 again. These are the results of real time actually, as you are able to see on your computer screens. The mechanical transmission, you will be able to see. Then the propulsion, the torque graph, and voltage measurement, everything is coming here. And the graph you and the signal you have taken on your trace graph, you can be able to see here. Say for example, in this graph, vehicle control and EMS, we have taken the DCM speed. So what signal we have placed inside it, you can be able to see with the help of the legend. Just to if you check on the uh, box of the legend on your speed graph advanced setting, you can have the legend as well on your screen, and you can add more graph in a single trace graph by adding a signal. So this is what the SCADA panel and this electric vehicle signal processing. I have just designed model and done the simulation for the same, and I have shown you the result in both the virtual hill mode and in the real time mode. So any of the participant, if you are facing any doubt, any difficulty in designing the model, or you are stuck somewhere, then you are welcome to ask like any of your doubt. And if not, then I'll switch to another model, and then now I will show you the another example model which is available in Typhoon Hill. And this is based on the actual library blocks of inverter and the motor as well. That's all I'll show you. But as I told you, this is only based on the signal processing components. In that in the model which I'm going to show you, this will a bit different from this model. So if you allow, and if you are okay with this, so shall I move to the next model? I will demonstrate the same only. I'm not going to, design and simulate that, because it requires around 3 days to complete that particular model. So I'll show you its demonstration in detail, and so that you can be able to understand and you can be able to feel the differences between the two, which I have completed right now and which is I'm going to show you. So dear participants, can I shall I forward for the next model? Shall I go for the next model? Okay. How many participants are there? Let me see. 30 only. Yeah. Actually, I'm not able to see the screen. Fine enough. There are 47, 48 participants. There's some chat also. Is there any ask question? No, fine. So fine. Let me go to the another model. Can anyone confirm me? Am I audible, Fazlus? Am I audible? Okay, fine. Thank you. Thank you.
Yes, sir. Yes, sir.
Okay, okay. Thank you. So let me go to the another model. Now, I'm just switching off my device right now, and I'll show you the another model. Let me once again share the screen. Just I am closing this, and this schematic also I want to close. I've already done it. Now, what I want to tell you is from the scratch. I'm telling you, just as you open this, the Typhoon Hill Control Center, you need to go into the examples, and with this, you will be able to open the, you know, the another model of which is available in the Typhoon Hill library. So let me tell you, just give me a moment. Yes, yeah. So you have to go into the examples, and there's a section of automotive in this, and this there are two example available. The first is the electric vehicle. Click on this electric vehicle, I mean, and open this, the open the model. Click on the open model, and you will get the schematic for this. Yes, this is the model, and here we have used the, you know, the actual inverter and the motor. I'll show you, and its application note is also available so that can be able to find out the more details for the same. So as you are able to see in this model, this is for the vehicle to grid and grid to vehicle operation, and I will show this when I run the model on in real time. And for this, we are having the grid and residential load, and we are having a charging station, and this electric vehicle. So what inside this and what this model is uh, illustrating, let me tell you. Actually, this is the basically the operation of electric vehicle, vehicle to grid and grid to vehicle forming operation, and this system basically consists of the three parts as it is showing on your computer screen. The first is the grid and residential load, and then charging station we have. Then the lastly we have this electric vehicle. So what inside this, and what we are using, what component we are using for this, you need to go for look under the mask, and in look under mask you can you will be able to having, you know, actual things which we have take here. So for this, if I talk about this starting from this grid and residential load, So yeah, here let me open it by just right click, mask, look under mask. The very basic components we have used in this, and here we are using a grid and residential load. We have named this subsystem as a grid and residential load, and here we are having a three-phase voltage. With this is the three-phase voltage source we have taken, and we are having the grid impedance. This is the grid impedance we have taken, and we are having the contactor with the residential load. So this is a contactor with this residential load. Okay, and then rating, if I talk about the rating for the residential load, so the nominal power for this residential load is 20 kVA. Here, let me show you. Okay, nominal power we have taken, and this requires a lot of dynamics and the time as well for uh, creating the subsystem and all. So just let me tell you the brief of this, and these are the ports. These are basically the electrical port, not the signal input port and signal output port we were using since 2 days ago. These are the electrical ports, and this makes the difference just because we are just giving the output of this grid and residential load to our charging station and then to the electric vehicle. So this is the grid and residential load, and I have just told you. And uh, if let me tell you more in detail. Basically, this is the detailed overview, I should say, of this uh, electric vehicle, and I will come on each and every block one by one. So let me tell you more about this model, and it shows basically the capabilities of the electric vehicle, and so we have used some components that are available in the microgrid library also. I'll let you know. Now let me tell you more. Actually, this model of electric vehicle is having the 270 kilowatt induction motor. Yeah, I'll show you in the induction motor here. You can see this one, but I will come to it in deeper side once. Just let me tell you the overview of this. So it is consisting of a 270 kilowatt induction motor with a 250 ampere hour lithium ion battery, and it is also consist of the 175 kVA battery charger that is implemented using the battery inverter component from the microgrid library. Yeah, this is here we have used this the battery inverter component, and that is the part of the microgrid library, and further has done the simulation also, I think on second day or third day, I don't remember exactly. So, and this basically supports the grid forming and the following modes for vehicle to grid and grid to vehicle, as well as for the UPS, that is uninterruptible power supply, UPS operation. Okay, and the powertrain control module, PCM, that is based on the field oriented control scheme with the regenerative braking capability, that is going to happen here. Okay, that I will come again on this in detail. And this model basically includes as well a 20 kVA load for simulating UPS mode, and this is basically done by switching the battery inverter to grid forming mode and disconnecting to the grid. And let me tell you one more thing. Actually, this example model of Typhoon Hill does not implement any specific manufacturer's topology for the drivetrain or for the battery converter. It basically demonstrates the use of ready-to-use power electronics and microgrid components in order to have build the model in the high fidelity and system level application. So for this, let me go in again to detail and come once again to the root. As I told you, this grid and residential load is having the 250 or 240 160 hertz voltage source with a RL section impedance, and the grid is basically connected to the rest of the circuit with the help of the contactor, and as it is showing in this figure. And next to the contactor, there is a 20 kVA load, this one. Yeah, okay. And which represents the household load, and that can draw the power either from the grid or from the vehicle battery. Now, if I come on more detail, as I told you, it is having the three main components like EV. If I talk about the EV, this is the EV, electric vehicle, and this is consisting of the lithium ion battery. Here it is, and three-phase inverter with LC filter and induction motor as well. So, and if I talk in the case of the charging station, so here we are having the battery inverter average. Right from the core, the component is available from the in the microgrid library, and it is implementing as a full switching model with its own control in both grid following and grid forming. And in order to scale down the inverter to 175 kVA, the component model is kept intact, and only the mass level parameters are changed here in this. And this where the parameters of this you can be able to see here, like the nominal power 175 kVA, nominal voltage is 240 volt, and the ceiling voltage is 400 volt. Okay, so these are the basically battery inverter changed parameters. And as let me tell you that the EV presented in this model is realized using a battery with the following parameters. So battery parameters in the EV, let me tell you here, you can see the nominal voltage of the battery is 400 volt with a capacity of 250 ampere hour. Okay, so now let's come to the electric vehicle subsystem. Yeah, already it is open. It is basically consists the EV model. In this EV model, we are having the connection logic and the control subsystem is also available here, and the measurement devices we are using here. These are the measurement devices. These and the meter split we are using. We have created this with the consumption calculator. This is the consumption calculator. Okay, here we are just doing some conversion, and the mechanical model blocks and the internal modulator of this three-phase inverter here is used. This This is the internal modulator of a three-phase inverter. We are operating our three-phase inverter in the internal modulator form with a carrier frequency of 20 kilohertz, as you are able to see here. Okay, and let me tell you the full description one by one of this. So, very first of all, just come to this connection logic. And before this, let me tell you, we are having the grid and residential load, then the charging station, and this is the electric vehicle. And in the electric vehicle, we are having the battery. This is being charged with the help of the charging station. And now this is the connection logic. Just let's understand the basics of this connection logic. And actually, what is happening here? Uh, we are using some logic gates and the like not and or operations just to create our logic. And the logic basically says in this like close the contactor. We need to close the contactor if the vehicle is off and motionless. So at that time we need to close our contactor, or contactor is being blocked by the charger. And we need to turn on the motor if the start command is on. Where is the start command? I will let you know in the SCADA panel. So we need to turn on the motor if the start command is on, and if the charger is not connected, then only. And charger is not connected. If the charger is connected, we can't run our vehicle. So this is the very self-explanatory logic. Like we need to start our vehicle only when the charger is not connected with the with our vehicle and with the supply. And block contractor from opening while charger is connected. So we need to block the contractor from opening while the charger is connected. At that time we can't open the our contactors. So and this is basic the logic in this the connection block diagram of electric vehicle for connecting the vehicle and disconnecting from the charging station. And As I told you, the block functions of that we need to connect the vehicle to the charging station in case of the vehicle is stopped, and it prevents the vehicle from disconnecting from the charging station while the charger is connected, and prevent connection to the charging station while the vehicle is running. At a time we can't connect the charger, and also prevent the motor from starting while the charger is connected. Okay, we can't start the motor as well. And if I go back to this control, this is basically the control which that is being implemented in this example model. So for this, the PWM references like these signals MA, MB, and MC. These are the signals that are generated by the PCM. This basically I'm talking about this. Uh, that's the control logic and the control. This is PCM, power control module, and IF. This is basically based on IFOC, and and it is showing as in this diagram the signals, PWM signals, and here are basically a three-phase meter component is used to measure the currents and active power flow between the induction motor and the inverter. This one, with the help of this three-phase meter, you know uh, we are measuring the currents and active power flow between this induction motor and this inverter. And the BCM, as I told you, this is the PCM basically employs a simple FOC, field oriented control based scheme, in which the measured three-phase currents, uh, the three-phase currents are being transformed into direct ID and IQ, that is the direct axis, and the quadrature axis components here, and which are then allow control with the help of the PI regulators. We are having the speed regulators, that is the uh, we can say the PI regulator. Here we have implemented this PI regulator, and the machine flux related to ID while the torque is related to IQ. Okay, yeah, this is flux regulator, this sorry speed regulator, and this is a flux regulator, you can see. And now the rotor flux angle theta is needed to convert from ABC to DQ here, and here uh, and then as I told, the rotor flux is being needed to convert from ABC to DQ and GQ to alpha beta, as you are able to see here as I'm just clicking on the cursor. And DQ to alpha beta transform is calculated the indirect FOC, and for the machine electrical parameters, and for the rotor speed and measured currents. So for this you are able to say this complete, I should say, the control block we have Typhoon Hill have designed. And for this, if you want to go in detail, you can go through the application note for this model that is available on the website of Typhoon Hill. Now let me tell you more about this. Actually in this, in the nominal voltage, as I told you, is 400 volt, and the maximum power is 270 kilowatt. Frequency and maximum RPM is 16950 RPM. Pole pairs we are taking two. So in this, the flux reference is generated in the flux reference block, and starts as constant value as phi reference. And say let me show you something which is available in the Typhoon Hill. Yeah, as I have just clicked on this open model, we need to open this application note also. I just forgot to tell. And here, yeah, whatever the things I am telling you about this model, I have gone through this application note and understood the things. That this is what I was explaining, and you can have the look in this, and in detail you can go through this, and you can uh, take an idea for the same here. The same thing like which is available and that I've shown you is available in this like application note. Yeah, this is the This is what I have shown you. The dynamics and the mathematics they have used, this have already been illustrated here. And this I was just explaining this to you, that if the flux generated is generated in the flux reference block and starts the constant value side reference, if the motor gets speeds up, then the armature voltage rises to the main flux. And this is the basically operation. I will just show you well when I will run the model, and I'll show you the results in the real time. And if the as it is being shown over there, if the inverter voltage is reached, voltage limit is reached, rotor speed cannot increase further. That defines the basically base speed, and this is given by w base. And the flux weakening method is also employed in this to allow the rotor to go beyond the base speed. Okay. And this is basically the torque reference is being calculated in the speed regulator. Let me show you. Let me show you here in the model. Just wait. Yeah. Here the torque reference is basically getting control, and this is basically the throttle by which we can, change and put the variations in our motor speed variations with the help of this. And this is the PI controller that is available in the Typhoon HIL library, and we have taken this from the library of Typhoon HIL only. And this is basically the torque power limiter, and we this is nothing, simply the C function. C function I have already told in the previous lectures of mine in the boost closed loop operation. And here we need to define some inputs and as well as output. Then there are some variable as well with us, and some parameters also. So this is what we need to define in the C function. And now how they are correlating with each other, that we need to define in the case of this advanced C functions programming. And this is a basically small program there, which is being calculating by taking all the parameters which we have defined in the input and output and in the parameters and variables form. So just this the concept, the theory I just told just before this is being implemented in this, like if the power is less than p minimum, then what happened, and then what is the next condition. So I'm not going in very much detail about the programming. So now let's get back to this model again. So here in the speed regulator, basically the output of the speed regulator is basically, you can see here. Yeah, this is basically the output of a speed regulator is a reference torque, which is further processed by a C block. Okay, fine. And this um, now it limits basically the this speed regulator limits the acceleration power to 270 kilowatt, and the acceleration torque up to 860 newton meter. And the limits the regenerative braking power to 60 kilowatt, and regenerative braking torque to 250 newton meter. And when it multiplies the resultant torque by the throttle, shows in the percentage. And the induction motor is loaded with the variable torque, and the mechanical part of the electrical motor is governed with the Newton's law of rotation. Let me show you. Yeah, the mechanical part of this electric motor is governed by this Newton's law of rotation, the generalized equation. And they have just processed with this and taking all the the equations they have flowed in consideration by taking the grade resistance, rolling resistance, and the wind resistance also in case of this electric vehicle running. Now let me go on. Now the main thing, the main I have just already elaborated. And let me go back to this schematic. And as I have told about this schematic operation, now I'm going to run this model basically in the real time mode. Directly I would like to run the same in the real time mode, and I will just tell you and show you its SCADA operations. Okay, if I'm not wrong, I have completed all this. So let me just connect once again with my simulator. Yes, let me go to this schematic once again. Yeah, I have just turned it off. Uh, wait, yeah, it's came now. It's fine. Yeah, it's connected. Perfect. So let me simply just compile this. Yeah, I have gone through all this control I have told and this connection logic. Okay, fine enough. And in the charging station also, I have shown this battery inverter. And this is basically the graded residential life inverter I have told you. Now just run the simulation in the real time mode I am running. You can observe the right bottom of your screen. It will show you the real time. So it's a heavy model, and so it may take some time, but it won't take more than 1 minute, as this is the, I should say, the specialty or the beautifulness of Typhoon Hill. In the real time, it is almost it never takes more than 1 minute. So the model is already compiled, and let me show you the SCADA of this. The model is getting automatically loaded because right now I'm connected with my real time simulator. Yes, so I'm ready with my model. Sorry, the SCADA panel. So this is basically the SCADA panel of the corresponding schematic that I've shown to you, and here you will be able to see the on the the charging block diagram that this is basically the DC fast charging. Oh, yeah, let me unlock it. This is a DC fast charging, and these are the some LEDs panel that will show you which mode your electric vehicle is working on. And these are basically the some buttons that are showing the operation modes. And just right side of this all, you will be able to see the electric vehicle, this dashboard, and the battery. So let me uh, toggle it full screen. Okay, wait. First, let me tell you. Yeah. So this is basically the dashboard and the battery you are able to see, and what inside this battery, what inside this dashboard. Let me tell you more. I'm just running this simulation in the real time. Just want to show you in this DC charging panel we are having this. Like the terminal voltage, the frequency, we can have the DC link voltage, okay, and the terminal voltages of like active power, reactive power. I'll be having all those. And after this we are having some status of this sorry, the LEDs are connected, and the logic is being implemented in these LEDs. Signal has been already added, so that is a part of designing, but right now I'm not designing the model, I'm just demonstrating you in detail. Say for example, this is basically a electric vehicle dashboard. So here you will be able to observe the speed which is going which is showing in the RPM, and the distance is being covered with the help of the electric vehicle. And there is a slider available with us. With the help of this we can vary its speed, and we can apply the brake as well. Electrical torque and the average consumption you will be able to see in this gauge. You can able to see the power and torque graphs as well in these basically XY graph of Typhoon Hill. And when I go back again, like in this panel here we are having the cart, and this is showing the battery over there. and the battery is having the DC bus voltage and the state of charge that is being displayed on while running the simulation. Right now, no results are coming just because I have not done the simulation. I'm just telling you in brief about the widgets we have used and what the signals we are using in this. And this is the bar graph that will show you the battery state of charge, that in the form of the display, that how much the battery is remaining, the how much the charge is remaining inside this battery. That is being showing with the help of this bar graph. Or got disrupted. Let me make it large. Yeah, fine enough. So let me tell you the working, how how it is working and how the regenerative braking is occurring in this. Till now, if you have any doubt in this schematic, you can ask me. Now let me run the model. So when I just let me tell you the operations I just forgot to tell you of this SCADA. Basically, it will work in the four, I should say, the five different operations. The first is the driving mode, in which induction machine will act as a motor, and the another is the regenerative mode, and in this machine will act as a generator. And EV charging mode, uh, basically we will show you the charging of the battery. Then vehicle to grid operation, where we support grid from vehicle to battery, and UPS mode, where we support load from the the vehicle battery. Then if I talk about the first in the drive mode in the dashboard, when we start and give the speed up to some exam like up to 80% or something, then we can show you the variation over there. And say for example, let me run the simulation now. Just let get into this. The SOC you are able to see is 80%. Initial value we have given is 80%. Now just we have run the simulation, but I have not run my electric vehicle. Let me go into this uh, dashboard, and now I am just setting up some speed. Say for example, I wanted to go up to 80% or this yeah, and let me click on this start button. So after I click on the start button, the start LED is glowing, as you are able to see, and the speed is increasing, and it is try to achieve its required speed. That is the desired speed, I should say, the speed of reference, which I have just applied here, that is up to 80%. And now, as you are able to see, the battery is getting discharged, and it has become 78. Earlier it was 80%, and these are the power and torque graphs you will be able to observe here. Now let me go back to the another thing. This panel, your battery, you are able to the flow of power is that battery to vehicle, and the battery SOC is 78.439 percentage. And this you can see the SOC, the battery is getting discharged as with the time. Okay, and you can see the flow of power as well. Let me go again inside this. Now the battery have achieved its desired position. Say for example, like 80%, I have given the reference, and it has been achieved and the distance and the speed is showing here, and the power and torque graphs is also visible here. You can observe these power and the torque graphs. And now let me decrease this speed and let me show you the regenerative braking. Now till now the SOC is 77.35%, and it shows clearly showing that the our vehicle is running and the battery is getting discharged. Okay, so say for example, let me reduce this speed to 20%, I should say, or 10. So now here you are able to see, as I just decrease the speed, and it is showing the regenerative braking. The regenerative braking is occur. Typhoon regenerative LED is blinking here, and you can observe the power and torque graphs in this case. And if I go back to the panel route here, you can see, you can observe, like the panel in this panel, battery panel, the direction of the power has been reversed right now. Okay, and you are able to see that the battery is getting charged like 77.1415. Yeah, it is basically the regenerative braking mode. And in this case, basically we use energy to charge the battery, and regenerative braking is occurring here. You are able to see here, and the battery is getting charged, and you can see the SOC right now. Yeah, earlier it was coming down, now it is getting charged. So this graph is going up with the time variation. And I've already shown you the power and the torque graphs, and this process will end up when, you know, the battery speed, yeah, will go to zero. Yeah, no, it got off. This Typhoon regenerative braking LED is basically got off, and we're able to see here. So now this is what basically now I am just stopping like my vehicle, and this is about the regenerative braking. And when I just go to this EV charging, let me show you this EV charging. Now, when I click on this EV charging, yeah, now EV charging will be the DC fast charging, and in this EV charging mode, the LED of this connected to the grid, and this grid to vehicle. Okay, we are just charging our vehicle. The connection LED is glowing over here. Like we have set up a connection between the vehicle and the grid, and grid to vehicle. The power flow you are able to see, and earlier we have given the reference to 80, and now it is getting charged. So it is getting 81.30.33. Now it is getting charged over there. This is basically the charging mode operation, and in this mode the energy will flow from grid to battery with the help of a charger. Okay, and another mode we are having vehicle to grid mode, and here we can click on this vehicle to grid mode. Yeah, now you know the cha- flow of power is reversed now, and this is the vehicle to grid mode. I am just simply clicking on these particular buttons which is available in the SCADA panel, and here in the vehicle to grid, in this mode we can support the grid actually. Okay, and you are able to see that here it's getting discharged, right? The SOC is getting discharged. In this mode we can support the grid, and the LED or the red LED is blinking, and it is showing the vehicle to grid operation is going on, and it show the charging as well. um, uh, Here you can see, so it is charging here, it is getting reduced, and okay, now it is showing here. So this is the vehicle to grid operation, as I have clicked here. Earlier I have shown to you grid to vehicle, and the last is the UPS mode. In this mode, let me click on this UPS mode. Yeah, uh, yeah, in this mode we are just we'll support the residential load and up to 20 kilowatt, and this is basically the complete operation of this electric vehicle. And as I told you yesterday also and today morning also, that in this example, we have taken all components, all necessary components into consideration. I missed this point, that's why I'm repeating. Signal processing block also has been used in this, while just to draw the controller. Yeah, just to draw the controller we have used this signal processing block. These all are the signal processing blocks, the blue green color. And the actual here in the last example, in the signal processing example, we have designed the battery with some dynamical equations, but directly here we are just dragging and drop the battery which is available in our library. And we are just taking the inverter and this induction motor as well, the actual components we are using this actually. And we have also used the signal processing components, and the connection logic, the control logic, everything I have just told you, and the charging logic also. Yeah, that's greater residential load. So this is all about this the model of electric vehicle that is being scheduled in the timetable of this workshop, like electric vehicle to grid and grid to vehicle operation. I have demonstrated here. So dear participants, your queries are welcome. Or let me go to the another model, the another example, like this that is available in the in our Typhoon Hill. So this is basically AC charging model. Here we have shown you, we have demonstrated you about the DC fast charging, and now in the another model, I am just going to show you the AC charging, how the AC charging takes place in the environment of Typhoon Hill. And in this, basically, we are not using any type of converter and the motor. We there in this upcoming model, we are just focusing on the charging logics only and the charging profile. So just I am shut closing this. If you have any query, you can ask. Then I am just moving to another model, the last model of this particular session. Then it will be done from my side, and in the next session you will be able to know more about the Typhoon Hill test ID. And let me close this. No, I don't want to save it there. This is an example, and as I told you already, we need not to save any changes in the example model. So now we are going to open another model, that is the AC charging model. So let me tell you, let me show you the brief of this model, the another model, and um, let me do one thing for this. Actually, this supports the configuration ID 3 in Typhoon Hill 402. So for this, I need to change in my firmware, as we have done yesterday also. So for this, I need to change the configuration, and for this, I need to have the configuration 3, and then only we can run it in the real-time simulation. Change configuration. Yeah, the firmware is getting updated and taking it to the configuration 93. Yeah, it is taking time around 5 to 10 seconds more. So now the electric vehicle AC charging I am going to show. Just let it complete first. It's fine. Okay. So basically, in this model, this as you are able to see on your computer screens in the yellow, text box, like this model describes the electric vehicle charging according to IEC 62196. So what is IEC 62196? You guys must be aware about it, and let me tell you about it one more time. See, it is basically a series of international standards for like plugs, socket outlets, vehicle contactors, and vehicle inlets, that defines the requirements and test for the plugs and the sockets as well, and another vehicle accessories for the conductive charging of electric vehicles. And let me tell you more about this example. This basically applications combines the electric vehicle AC charging, as I already told, and the IEC 62196 type 2 connector is modeled in this example. Basically, yeah, there is a connector. There are various connectors for charging the electric vehicles. Here we are using a J1772. This is a J type of plug which are being used to charge the electric vehicle. I'll show you its graphics. I will show you. Okay. So here we have modeled that 62196 type 2 connector in this example, and the communication between the EV charger and EV is performed, and with the help of PWM signalization over control pilot as per the IEC 61851 and J1772. And about the IEC 62196 is, I have already told, it is basically a series of international standards, and it is maintained by the technical subcommittee of SC23H for the plugs, sockets and outlets of the International Electrotechnical Commission. And as I told, like for the control pilot, we have taken as per the IEC 61851, and IEC 61851 is an international standard for electric vehicle for conductive charging systems, and it is one of the IEC's group standards for electric road vehicles, let me tell you. And also it's the responsibility of IEC only. And about J1772, it is known as the J plug charger. So what is actually, let me show you on internet only, like uh, sorry, what is J1772 mean is, you will get to know what I want to say. Yeah, yeah, this is the basically J1772 is the charger, like it's a J charger, so we can, it is almost in the form of a J, so that's why it's called as a J charger. And about it I have already told, that is a known as a J plug, and it is a basically a North American standard for electrical connectors for for electric vehicles. So this is what I want to show. This we have modeled this in this example. So here, as you are able to see, we are having the public grid and charging station, the cable and the electric vehicle. And let me tell you brief about this is, this accompanies the electric vehicle AC charging, as I told, and the communication between the EV charger and the EV is performed using PWM signalization, as I've already told. And let me uh, go in detail about it. So for charging the electric vehicles, let me tell you concept. For charging the electric vehicles, and exchange of information between the EV supply equipment and the EV is needed, just to have a defined condition like charging power and another things like battery voltage and current. This signaling is based on the international standard, uh, and which can be distinguished in the four modes, the first is for the three for AC and one for DC charging. And this I'll show you uh, in the application note. And for to applying the DC charging, significant information exchange between the battery and the external power supply is essential. Thus high level, I should say, the high level communication is needed. But in the case of the AC charging, just the pilot signal is necessary. And most stationary installed EVs apply mode 3, as it allows the, the highest flexible and high charging powers. And I will show you this in the application note that describes the procedure of signaling on the contact pilot CP, and for AC charging according to IEC 62196 mode 3. Okay, now let me come to this model, and here you will be able to see, in this model, the connection between the EV and the charging station. This is EV, this is the charging station, and between these there is a cable. So the connection between the EV and the charging station has been realized with the help of a direct connection that can be interrupted by a SCADA control contactor. And let me show you. Which in the cable we need, I need to show this. What I want to show you. Yeah, this is basically the CP, the control pilot over there. Okay, so that can, as I told you, that the connection has been interrupted with the help of a SCADA controller. When I will run the SCADA, I will let you know. And in this figure you are able to see the that is the signals being showing for the CP, and then PE and PP, and these are control pilot and the proximity pilot, and the SCADA inputs for the corresponding car connect and cable connect is showing here. And a resistor, as you are able to know, the resistor between P and PP on each side of the cable codes the maximum allowed current, that is the IMAX cable. There is a resistor over there, and at the end of the PP and P, yeah, here. Okay. And now the measurement of the resistance is included in both in the EV and AC charging subsystems. You can able to see. And yeah, this is the some contactors. The one contactor we have taken here, that is being controlled with this. This is basically the tag, the signal tag we are using. Okay, from and go to. So here, what is happening in this? Let me tell you the operation of this. Wait, let me make a zoom. Yeah. So in this, what is happening is, after the maximum current carrying capacity of the cable is detected, the EV charging requests need to be signalized, and that is being done with the help of a CP, that is control pilot. And on the CP pin, the charging station provides the PWM, like the pulse width modulated signal with an amplitude of plus minus 12 volt. Okay, this is the generate PWM. We are generating the 12 volt reference here, as we are able to see. And with the frequency of 1 kilohertz, and this is evaluated on the EV side as showing in the circuit. And when the car is connected, the resistor, this R2, yeah, is it able to see the resistor here. uh, in that side, in this as the resistor as I've shown you. Okay, so let me tell you the operation in this application note. I have not opened the note. Yeah, here it is. Yeah, this is the operation you can go through when you require the same. This is the this being the model. This is the model I was just explaining you. So as I was saying that when the car is connected, the resistance R2, of 2.7 kilo ohm is, and that is in parallel, and the VCP car drops to 8.8 volt, which states that the connection is in proper, connected proper. And with the charging request, EV closes the contactor as car. Okay, you know uh, and after just this is the resistor R2. Yeah, you able to see here properly. This is the resistor R2, this is the contactor S car. Okay, it's connected in parallel, and which states that the connection is properly. With the charging request, as it is logic is explained over here, the EV closes the contactor S car, and our contactor is 1.3 kilo ohm is in parallel with the R2, and this reduces the VCP to 5.6 volt, and that indicates that everything is set up for the charging. And this is being processed with the help of a C function, so that is all being taken into consideration in this schematic. And just let me take you again at this the schematic. So if you must be wondering, like, in this case we are also here also we are not using any type of the motor and the generator. So let me tell you one more time. Here we are just focusing on the charging profile. Here we are just focusing on the charging profile only, and we shows the how the AC charging takes place. Okay, this is basically the components, the generic components of the battery, energy storage library we have used in this. And this is basically the detected duty cycle and the PWM generation. And here we are using this battery ESS for in the block diagram of this electric vehicle. Then we have a cable modeling, In the case of cable, we have taken into consideration some contactors and some resistors. Then in the charging station, we have developed the logic for connection, for connecting and disconnecting. And in the public grid, just we have used the public grid that is available in the like example of sorry, the library of microgrid. That is the one we have used the grid impedance model, and it shows basically the input and outputs that are defined in the corresponding GUI. Yeah, that's grid is available in the microgrid library, and this is its corresponding, user interface. So this is all about the schematic. Now let me run this uh, model in the real time. Just click on it, as I've already changed its configuration. And for this, let me take you on the SCADA. And in this SCADA, you will be able to get to know about the how the charging it's taking place, how to connect the charger and all. So everything is available in its SCADA panel. And it's with the help of its graphical users interface of SCADA, you will be able to know more in detail. And what the thing I want to uh, tell you. See, this is the SCADA panel of this particular this electric vehicle model. And here, uh, let me make it zoom. As you are able to see, there is an option of this is the EV UI. It's a EV user interface, and this is a cable basically interface. And there is a provision of connecting the cable with the charging station and with this electric vehicle. And here you can on and off your, like, make the connection, and you can disconnect your charger as well. And there is option of charging. You can make your charging on and off if your the charger is connected or not. And then you will be having the grid interface that shows you the grid voltage, grid frequency, and the current, and grid active reactive powers, and the grid current. As battery inverter is also being displaying here, and some other EV internal components. So let me run it, and let me show you the the fast of the operation. Let's go to the contactor, and I want to make it close this one. Connect the cable is connected, but charging is not taking place. Yeah, as you are able to see, yeah, which the cable is connected. Okay. Just give me a minute, wait. See, you are able to see here, like, uh, in the case of this, when the let me take you at a full screen. uh, yeah, as you are able to see here, the charger is connected with I have clicked on this connect, which is connected with this electric vehicle. And the charging is going on, and I have just connected it on, and the charging is going on and the time, the what we call it as estimated time is showing here, the time remaining. It's like so 0 hour and 55 minutes, and the battery SoC is also showing here, and it is displaying like 50% and 51% of what, and the grid interface and the grid frequency is also you can be able to see, and the EV VCP charging station, the PWM signals you are able to see here. This sorry, the battery inverter is also you will be able to see. And you can this is just a glimpse I can show you. I am just showing you of this color panel, how it is working, and how you can work on this. If any one of you is working in the field of the electrical vehicle, so let me tell you, the Typhoon is will be one of the best solution for you in the application of electric vehicles. Particularly specifically I am talking about the electric vehicles, and for power electronics, and for microgrid also. And likewise, like in this you will be able to make the changes in your example models, just by copying the example models in your working folder, as I have told you, like how to do it. You can be able to make the changes in your model. You can implement your own algorithm uh, on which you are working for, and you can take the help of this example models, copy it and paste it in your working folder, make the changes in the control algorithm, make this model as far as better as you can for your research purpose, and publish the papers to which you can have a good provision, like in the field of power electronics, electric vehicles, and power systems, and microgrid as well. So this is what I wanted to tell you about this model, and this is generally and specifically, I should say, uh, based on the charging profile of electric vehicle. So let me go to restore default zoom level, toggle full screen mode. Yeah, fine. So this is all about the AC charging example, and let me tell you one more thing about the Typhoon Hill. Uh, so it will be very very helpful for you. Fine. So if you have any doubt till right now, you can ask me. Typhoon Hill Academy. Yeah. So here, as it is already been told you, but let me tell you in detail, more in detail about this. What I want to share with you is the very beneficial thing for you in the Typhoon Hill Academy. For Typhoon Hill, we can have different courses. Okay, if you want to learn more on Typhoon Hill, you can have all these courses like AC/DC converter, AC converter, or on microgrids and DC/DC converters, Hill for microgrids, Hill power electronics, Hill fundamentals, and many more. These all are based on the journal and the current scenario on which the research is going on, and it will tell you about the provision to work in the field of Typhoon. Say for example, the very first course you need to have is the Hill fundamentals, and for this let me tell you about one very good specialization, that is the specialization program, that is Hill Specialist 2.0. And for this, what you need to do is, for being the Hill Specialist 2.0, you need to have these courses, these 5 courses, and you have to watch all the series of episodes, the lectures I should say, that are being available in these courses. And after, say for example, there is a course of Hill Fundamental, and for Hill Fundamental, you have to go to this course, and you have to take this course, and uh, you know uh, qualify its quiz. So then you will be able to complete this course. As likewise, you have to complete all the courses for this, Hill for power electronics, for microgrids, and for test automation or communication protocol. So you can have all these courses, and after completing these courses and cracking the quiz, you will be able to as a hill specialized, and you will receive a certificate from the Typhoon Hill, directly from that Typhoon Hill Novi said. And for that you need to just complete the courses, you need to watch the videos completely, crack the quiz, then you will be able to get the certificate. Say for example how to take all this, and like say for example, like they have already told about tell about this courses, that how to take the course, how to earn a certificate. So let me brief you out. Say for example, if you want to take the Hill Fundamental course, so just click on the Hill Fundamental, and so there will be the option of like login to enroll will come in on your computer screen. So then you can log in on this login to enroll, and I've already, yeah, so I have already completed this course, so it will not, yeah, it is showing complete in mine. uh, Now if I say for example, if I would not have been taken this course, and there is option of take course available over here, then I need to click on the take course and started watching the videos. Say and then after this you will have to give this quiz. And let me tell you one more thing. Say for example, if you are giving a quiz, or if you are attempting a quiz and you will be not able to clear in the first attempt, then there is no need to worry. You can have the n number of option with you. The only constraint is there is a gap of 2 hours between the two attempts. So after attempting, if you are not able to qualify, just attempt it one more time after re-watching the videos and all. So with this you can complete all the quizzes and all the lectures, and you will earn highly specialized certificates. So this is what, and I just want I'm just pasting this link in the chat box for Hill Fundamentals. Yeah. Oh, there must be some question. Have related papers as well, right? Yes, okay. It has been already answered from Samshay sir. So now this is the link which I have posted here. You can click on this link. You can register yourself, and you can have certificate earning on this. Okay. Now, sorry. Yeah. So in this fashion you can earn the certificate, and you can have the courses as well. There is one specialization is for Hill specialization program, and for the another is this converter circuits fundamentals. Okay, and you can have this also, this specialized program.
Sorry to interrupt in between.
Yes ma'am.
Shipra papers, do you want to get to know that is there any published paper regarding electric vehicle in Typhoon Hill that you are
Yes, ma'am.
asking or something else?
And I'm asking regarding the work examples that has been discussed in this overall session. So, are there related papers where people have worked
Related
exactly based on these examples?
No, related to this example, it is not available. But if you want to have, there are other research papers related to electric vehicle, which the researchers have done using something. So they that are present in published papers on website. I think Salim sir, you can show them in
Yeah.
published paper. There are number of papers regarding electric vehicle battery management testing. So there are number of papers present using the Typhoon.
Okay, ma'am. Thank you.
So you can explore that. But related to this example, this is just an example just to show that what are the things which we can do. And using these examples only, researchers have got their publications using the Typhoon here.
Okay. Okay.
So
Thank
inside the published paper, there are a number of papers. He is showing just the location to you. And
you. Okay.
in that location, you can go and search each paper, and whatever is according to your requirement, you can go ahead.
See, you can go to the Typhoon Hill and website and go to resources. And once you go to this documents, Then there's a documentation, knowledge based white papers and published papers as well. So here you can have a look on the published papers, and you can take it for your reference. I'm just posting this link also in the chat box. This, okay, this is latest paper as I shown here. I just do a sizing procedure of reactive electric spinning, some of the research area of any person over there. And there are a lot of papers like available here. Yes, but they are like showing right now it's showing 1 to 10 and it's up to 531 entries are there, up to 54 pages. You can explore it, and you can have the paper for your reference as well in this. Uh, so
Okay,
uh,
thank you.
yeah, yeah, most welcome. So for this session, I am done, and I have in this. Let me summarize that in this we have completed the signal processing in SCADA, and we have shown you the demonstration of vehicle to grid and grid to vehicle, and the AC charging example. So right now, if you have any doubt, like you can ask me, or if like I, I request Khushbu ma'am or Shamsher sir, if they want to add something, they can add, or we can have another session at 2 p.m. and it and this session in the upcoming session, the Khushbu ma'am will take this session, and she will be coming up with the Typhoon Hill test ID, and she will let you know the more advanced features of Typhoon Hill, another provisions also that uh, is available in the Typhoon Hill. Okay, so now this is a query time. If you want to have any of the participants, please ask.
More to add to Dr. Salim that
Yeah.
he already told you about the quizzes and the fundamentals. I request all the participants, you still have the 15 minutes time. You can log in, and if you are facing any issues, so in the lunch session, we can look after that, because those quizzes are compulsory. Means compulsory means in order for your professional skills to earn the certificate. So we have five quizzes, question papers are there. We want all you to explore the five courses and go through the quizzes. So first quiz you will give for Hill Fundamental. That because Hill Fundamental is almost two, three, one day, first day was the very first day was the topic. And regarding power electronics, it was the second day session. Regarding the microgrid, you explored third session. So three courses we covered. Also regarding the communication protocol, Shamsher Ansari sir already described about this microgrid toolbox and communication protocol. A little bit if it is required exploration that I can give you. So now so all four courses you have done. The last course that is left, that is test and automation, that you will be doing with me today in the second session. So I think these are the five questions paper which you need to qualify. Please try to log in if you face any problem so that we can discuss in the second half. We want that participants should come up with some of the certificates. That's all from my end.
Yes, thank you, ma'am. And so I'm still waiting for the queries. If someone is having any query, and let me tell you some more about the exam. Yeah, just give me a minute. Okay, let me come to this examples. Say, for examples, as we have already told you about this, but category wise I would like to highlight here, if anyone of you is working in the field of aerospace, you can go with the example. This is the very beautiful block, I should say, which is available in the Typhoon Hill, and that is the ready-made examples are available, and there is no constant of taking this into your research, and you can copy and paste it. You can modify it as per your control algorithm or as per the design requirement of your plant. So this is for the aerospace. गए होंगे. So this is This is for the automotive, and in the automotive we have shown you the electric vehicle and electric charging. That is we have already covered, and this is for the basic electrical circuits. You can take the communication protocols that has been the library has been already covered by with Shamshed San, and this is these are the examples. If anyone of you working in the area of Modbus or the the EC C37.118, that is PMU, and if anyone is working on 61850 in the communication protocol, IEC 61850, GOOS, MMS, and PV is also available. The Modbus and the serial example is also available. These all are available in the communication protocols. Yes, we have already touched with this electrical drives induction motor. Say for example, we have gone through this induction motor closed loop, and here there one more example, induction motor closed loop with 3-level inverter. You can go with this thermal model and calculation. You can also have the example model, and the MMC is also being given in multi-level model, multi-level converter with induction motor control. That is also given in the that induction motor example, electrical drive example. Okay, these all are examples which are just currently based on the current scenario on which the research is going on. And now for this general power electronics, there are some more examples which is based on the three-phase rectifier, single phase rectifier. These are very basic example, just with the beginning and with the scratch. If anyone want to one in the area of power electronics, they can have a look for the single phase inverter and the three-phase inverter, and they can go with this. And there's an option of grid connected inverters, and there is MMC and HVDC, like back to back converter. The DFIG is also given over here, and if anyone is working in this area, you can go with this hardware in the loop. This I'll take up if time permits me, then I'll take up the CHIL demonstration in the next session. If time permits me, then there is how to examples that is basically consist of the basics of like the examples like electric vehicle SP we have designed, and we have designed this, and this one is also we have covered boost advanced closed loop, and electric vehicle SP, this is what also we have covered. And marine subsystem, if anybody is working in the area of marine, they can have these examples. This will help you out. Medical devices, there is one example of HUD model, and one can have a look on this. Then microgrid, that is already being covered with our colleagues. And the power quality, yeah, there is a very good example of DVR, that is the dynamic voltage restorer. You can have a look on this. And uh, like uh, uh, for power supplies, this is a one welding inverter. And the power systems also, yeah, there is an example of IEEE 34 node bus islanding, and which consists of the artificial neural network incorporation. And another automatic recloser and distance protection relay is a very good example. You can have a look on this on the different form of the examples available here. So this is what